Martin Gardner's first publication in Scientific American was on flexagons. And we have a flexagon team at Georgia Southern. The co-authors for this paper are listed. We also have another paper coming out, or came out 2012 in the Martin Gardner Mathematical Association of American Tribute. Emil's here. His talks are going to be at 2:30 Saturday afternoon. It would be a good one to see. Hua Wong is our other member, and he has made some nicer theorems from what you'll see today. He's closed some algorithmic type theorems. And a couple Georgia Tech students that got us started back in doing this again. Regular flexagon has 3 colored faces. I'm going to talk about the first 9, and then the second 9, and then the second 9. And we'll work with flexagons of order 3, 6, and 9, and we'll finish with those of 12 N for all N. Arthur Stone's first trihexaflexagon looked like this. He pinch flexed from the yellow face into the blue face into the purple face, and then pinch flexed back to the yellow face. The Google Drive icon and the recycling symbol are examples of trihexaflexagons. My goal was to count the number of initial faces where you don't count translations, and the mathematical faces where you do count the translations of flexagons of order 3N for all N. The goal, we mimicked the 1979 paper for N equal to 3. We had complete success there. Then we tried the same text for all N bigger than 3. And for initial faces, we were successful. And for mathematical faces, we got some problems. This is the Tuckerman Travers from 1939. Concentrate on the yellow face of the flexagon. And the moon is at the center, and you can flex it to the other yellow face that will bring the planets together. But you can't get the sun into the center until you add 3 more, another face, 3 more faces. And with the 15 mathematical faces, we can get the sun, moon, and the planets to all come to the only on the yellow face. Only on the yellow face can you get those 3 figures to come into the center. I go with the paper by Oakley and Wisner where he doesn't allow turning it upside down. You can turn it upside down and get the sun to come together in the center. We only allow rotations, but they don't count as separate mathematical faces. And we'll use the pinch flex from 1939 and then the V flex from 1963. Putting these 2 flexes together is what we'll be doing, looking at all possible faces. This is the 1979 paper. We're going to start with face 0 and stay on the red cardioid as we come around and go back to face 0. In doing so, the monochrome colors will stay the same. But if you get to face number 5 and take a shortcut over to 9, then it will add 5 to all the numbers on the triangles. And 5 and 18 are relatively prime, so that face 9 there actually has 18 copies on top of it. The 9 that shows in the traverse is an initial face, and then there are 18 copies of it for the mathematical faces. And it was so easy to find. I'm trying to apologize for how we screwed this up, but it was so easy to find these translations. 5 and 18 are relatively prime, therefore we can multiply by 18 our final answers. At least 189 of the initial faces can be multiplied by 18, but 6 of them are symmetric. They're so symmetric that that once you've added 1 to each triangular face, it will come back and start repeating itself again. That's a hexaflexagon. The nona is what we were trying to do. We were trying to count the mathematical faces on the 9-face flexagon. We spent all year getting 100,000 initial faces. 15 of them are symmetric on this one, 15 symmetrical faces. So by adding 1, 27 times, we get to multiply by 27. And the symmetrical faces, we can only multiply by 9. Oops, not so fast. Ralph Jones says, where did you show you can add one to each face? And I said, we can't. Oh, but we did it for the 9-face one. So coming down the left side is from face 0 to face 9. Coming down the right side from 0 to face 12 is the harder path. The harder path around there. And lo and behold, the numbers on the triangles end up being off by 13. So 13 and 27 are relatively prime. You can just go through there 27 times and get 26 more face number 9s. And so that number is correct. This is for all n for the initial faces. And if we could prove that we can always translate by 1 for n equal to 4, 5, 6, and 7 forever, we would be done. So if the conjecture is true, then there'll be 2 billion faces on the 12-face flexagon. But Ralph kept us honest, and we can't prove that we can slide by 1 for any triangle. Thank you.